Okay, so today we will be talking about solar storms and Doomsday. Cheerio. The Sun has a magnetic field much like Earth's. However, over time it gets stretched and twisted, creating loops such as these. When these loops get stretched further out into space, charged material from the Sun follows their paths, and these are solar flares. When one of these loops snaps, the charged material is thrown out from the Sun, and this is a coronal mass ejection. They travel at very high speeds and can move in any direction from the Sun. They have much more energy than solar flares and occur much less frequently. This is the coronal mass ejection from 2012, and you can see that the mass moves straight out from the Sun.
The impact of the CME is dependent on the density of the particles. This equation allows us to calculate the density at any distance from the Sun. That's shown by R. This is providing that you know the initial density of the CME, which we understand to be an average of 10 to the 9 particles per centimetre cubed. But when we use the distance between the Earth and the Sun as R, we actually found the distance to be negligible, and the distance remains at approximately 10 to the 9 particles per centimetre cubed.
The magnetosphere, what is it? The magnetosphere is basically the predominant effective magnetic field surrounding an astronomical body. For Earth, it is the magnetic field generated by the Earth's core. When solar winds push against the magnetic field lines, sometimes they have enough pressure to snap them, which folds the field lines around the back of the Earth and focusing all the ions into the north and south poles, ionising the atmosphere, creating the auroras, which you see in this picture.
So because we're meant to be a pretty intelligent race, we like to know stuff, and one of those things is how far out the magnetic field lines stretch in terms of, so we can figure out where they're going. So we need to find some equations to do that. So to do that we need to use some dimensional analysis, which is a standard issue units to make formulas, like these ones you can see here, which are all really horrible and make some people want to cry. And then you can rearrange them and it makes this, which still makes a lot of people want to cry. So, you know, it's still not too nice. But from this, we can actually get some useful stuff, like the graph here. The rate of mass is shown and the other stuff is shown, but these are arbitrary units along the y-axis, which is that one over there, due to the fact that dimensional analysis does not give you constants. So this actually shows that as it gets faster, it does reduce the amount of the length of the magnetic field, but from there you also see that it gets pretty negligible towards the end.
Right, so in 1989, a medium-sized CME hit the Earth's magnetosphere, directed at North America. It caused widespread power outages for several hours. Also, in Quebec, Canada, it shut down the hydroelectric dam, leaving 6 million Canadians without power.
Okay, so this is Earth's magnetosphere normally, and as you can see, the red bit is pointed towards the Sun, so that's got a high amount of particle density, and then you've got the blue and slightly green tail going away from the Sun, which is an area of lower density. So this is without any CME sitting, this is just us travelling through space now. This is the CME that hit Earth that Charles showed you earlier leaving the Sun. This is what it did to Earth. You can see that there's slightly more particles around the front of Earth, but not too many. It's not really affecting the magnetosphere too much. Now, there was a CME in 1859 called the Carrington Event. This was the largest CME ever recorded. It was twice the size of any other recorded CME. And if it happened today, basically everything that was on mains power would kind of run out of battery or just stop working. That's what it did to the Earth's magnetosphere. As you can see, the deep red shows the massive amounts of particles that hit Earth's magnetosphere. And the fact that the rest of space is coloured in red shows you how many particles are flying through space. And it's kind of lucky that no one was in space at the time, because that wouldn't have helped them at all. Right.
Many naturally occurring events exhibit the same kind of distribution where less severe events occur much more frequently than more severe events. This can be seen on a graph such as this, where the less severe events are part of the body in green and the more severe events are part of the tail in yellow. This can also be represented by a function where, in the case of CMEs, the energy is put into the function in joules and the frequency comes out in the average, the frequency is measured in the average number of events per hour. There are two important values in this equation. The first determines the steepness of the graph as represented by alpha and is called the power law index. The second is a constant c which determines the height of the graph and is used to calibrate the function so that the result is a reasonable number for the frequency, since the energy and the frequency have different size values. An important property of this power law index is determining the mean value of the graph, which tells you the average severity of an event. Well-defined means that it's not infinity and it's not zero, i.e. it's a useful number and you can use it. If the mean isn't well-defined, then the graph will be less steep, and all events that are represented on this graph will wipe out all life on Earth. If the mean is well-defined, then the energy quickly decreases with frequency, so that at high, that's meant to be wrong, it has to be the other way around. High frequency events won't do any damage, and you have to have a very, very, very infrequent event to do any damage. And luckily for us, the experimentally confirmed value for alpha is 1.7, which gives a well-defined mean, and we don't all die, hence we're all sitting here. The final graph for this function shows that higher energy events, those that can do damage, occur on the order of hundreds of years, whilst lower energy events happen on the order of days. This graph can also be used to calculate the energy of events given a known average frequency, such as an event that occurs on average every week has an equivalent energy to taking all the uranium on Earth and using it in nuclear reactors. An event that occurs every 10 years has enough energy to create a 15-kilometre deep, 1,200-kilometre wide crater on the Moon. An event that occurs on average every 10 trillion years has enough energy to power the Death Star super laser to destroy Alderaan in approximately 3 seconds. Thank you for listening, and I'd like to thank our mentor Laura Cuffley and our lecturer Professor Matt Brown.